Good. I hope you can see my slides. I hope you can hear me.
Yes, I can see your slides and I can hear you.
Very good. Then welcome all of you to my talk. It's a pleasure to be here. Thanks for listening. And thanks, Marcin and Jurek, for putting together these very nice loop quantum gravity sessions. It's much needed in these times where we can't really meet. Thank you. The work that I'm going to present is in collaboration with two students from Erlangen. Refik was a master's student, Johan is a bachelor student, and there will be two more members of my group speaking today. Robert and Konstantin are both PhD students, and they will speak about something different. I'm afraid to say they will speak about more sophisticated things than I will, so it's going to be maybe more interesting because I want to talk about something very simple today, fermions in loop quantum gravity and their spin. And there's one little point of contact with the next two talks, namely I will argue that fermions in loop quantum gravity are extremely natural, and so in the complex variables that Robert considers even more so, and certainly in supergravity even more. So what am I going to talk about? Why am I doing this? Well, we are all looking for hopefully some big effect from quantum gravity. So either something that's obviously wrong that points us in a better direction, or something that maybe surprisingly explains something about nature that we had no explanation before. And to find something like this, I would argue it's a good idea to go to a place where we go close to the characteristic features of loop quantum gravity. And I would argue that one place is coupling of fermions, because fermions are natural in the classical theory. Ashtika's original variables are the variables that couple to the chiral fermions, and they are natural in the quantum theory. In particular, or on top of that, there's also the fact that they couple very tightly to gravity already at the kinematical level. So before even implementing the Hamiltonian constraint, I can already see some interesting things. So, and then the hope certainly is that this is robust. Most of you know loop quantum gravity extremely well, so I will be very brief for those that don't. We are talking about a canonical quantization program, but with a phase space that looks like that of a gauge theory, or rather is embedded in that of an SU2 Young-Mills theory. So in particular, one of the coordinates on phase space is an SU2 connection A, the Ashtika-Barbero connection. And the SU2 comes about as the essentially the stabilizer group in the Lorentz group of some time-like vector, and that is used in loop quantum gravity to do a partial gauge fixing. Loop quantum gravity takes diffeomorphism covariance as seriously as possible in a canonical setting, and diffeomorphism covariance suggests, for example, that one should use something like Wilson loop observables for the connection, because they can be formed without using a metric. And mathematically, this seems to imply that these Wilson loops act as creation operators in the quantum theory, creating line-like, loop-like excitations, and eventually then also networks, the so-called spin networks. Dynamics is in three sets of constraints: Gauss, diffeomorphism, and Hamiltonian constraint. And I will say sometimes kinematical, and then I mean that I'm maximally concerned with the first two of them. So I want to argue that fermions are natural. In fact, they are almost so natural that one doesn't have to put them in by hand. Imagine we cut a Wilson line open like here, then we get a line with two endpoints. At the endpoints, we now actually have to choose the indices. So at each endpoint, there are two states. There's a little Hilbert space with two states. under gauge transformations, these states get rotated into each other, just like a spin 1/2 fermion would under rotations. Moreover, if we look at diffeomorphisms that swap the places of these fermions, then interestingly, if we are in the same state at both ends, then the state picks up a minus sign under this flip. And so implementing the diffeomorphism constraint, those states get mapped to 0. And one is left with a sort of anti-symmetric state where we have different states on both ends. And this looks very, very much like a singlet state of 2 spin 1/2 fermions. Unfortunately, I don't think in this form this carries through because, well, for one thing, if we don't put in some dynamics for the fermions, then I don't see how this can work out in a theory where the Hamiltonian just has gravity dynamics. There's something funny going on with gauge invariance when we just have open ends. And the statistics argument, unfortunately, also doesn't go through all the time because I can easily find gravity states with open ends where the open ends behave like bosons, unfortunately. So let us look at what is usually done in loop quantum gravity. And that is a very beautiful story that many people have contributed to. And I just give you the upshot for a Weil fermion, let's say, for simplicity. So one lesson learned is that it's best to consider half density variables. So one distributes density weight between the field and its momentum. And so then otherwise it's the thing that you would expect. So we have these standard anti-Poisson relations. And in the quantum theory, one sort of implements these. And there's a thing that is a little subtle, and that is a story in itself. Namely, it is very nice and natural in a sense to also take a limit in which one, in a sense, shrinks the support of the smearing functions such that one ends up with fields that have anti-commutators where there's a Kronecker delta instead of a delta distribution. And there are things to say about this, good and bad, but for this talk, I will just accept that we're going to do it like that. Then the Hilbert space is just tensor product of gravity and a fermionic Fock space. Now, the fermions then transform under gauge transformations, and therefore to form gauge invariant states, one really has to cut open the Wilson lines and combine gravity and fermionic states like here. So in a picture, the fermions sit at the ends, at open ends of the spin network, and therefore give a gauge invariant state. It's interesting to note that this creates entanglement between the two. Actually, the entanglement is maximal. So very strong coupling between gravity and matter already kinematically. So one characteristic feature of fermions is that they have spin. And I would like to ask the question, can we define the spin in loop quantum gravity, and does it have the expected properties, or does it work very differently? And there's an obvious problem because spin in flat space-time comes from a global symmetry. There's Poincare symmetry, so there's a rotation group inside there. You have to single that rotation group out by picking a time-like vector that splits in rotations and boosts off. And then you can you have the generator of these rotations, and that would be your spin operator. And if you boil it down here in case of a Dirac spinor, then in the end you get a Pauli matrix acting on some chiral components, so exactly what you would expect. Now in curved spacetime, as I said, no global symmetry, but we have the local Lorentz invariance. And there's a generator of that on the fermions that I call Sij here. And we can do the same pattern. We can take this internal time-like vector that we are using in loop quantum gravity that defines us the rotation part of this. And then we can work out what that is in terms of the fields. And then we have an operator in loop quantum gravity that corresponds to a spin. And indeed, first check seems to work out because you get commutation relations that look very much like spins at points, and you get a spectrum that has something that is exactly expected for spin 1/2. But is that really a good analogy? Because you see that object here that has an internal index, so it's not gauge invariant, it's not a tangent vector like we would expect spin to be. So what is this? Well, in the theory, we have the frame. So we can always go back between tangent and internal space. And in fact, we can convert this spin operator into a tangent space object. And that thing is gauge invariant, is a tangent vector. So that looks more right. But it's not loop quantum gravity friendly because, for example, it has this tangent space index, and we don't know how to deal with this under diffeomorphism, group averaging, and so on. So how can we also don't have an operator for this frame? So what do we do? Well, as long as we look at inner products, like for example the length of this spin, then we can forget about the distinction between tangent space and internal space, because we can the two products will be the same. And so that is the solution we take here. We do calculate with the gauge variant spin, but we only consider gauge invariant quantities. And then physically, at least classically, it's the same. So now, given that, does the spin that we have defined function like in quantum mechanics? Well, we have already seen the commutation relations. They seem to be promising. But in quantum mechanics, one also does one more thing with spin. One adds spins. And we would like to do this here. But to do this, we need to, first of all, bring them to the same point, because we have curvature. And so we cannot just add spins from different points. And so luckily, we have a connection. We suggest we can take the Hbac connection to do this. And then to, for example, measure a spin at a point X and then transport it to a point Y, we would have this operator here of the transported spin. And that certainly depends on the path E that we take. And when we have done this, we can do this for several spins, and then we get can also add them at the joint endpoint of these paths, and we get a total spin. And now there is something subtle going on here, although it seems very simple, everything, because this holonomy that is here in front, that's not just a matrix, that's an operator valued matrix. So this really is an operator, and it's not by any means obvious that this parallel transported spin is a quantum mechanical spin again. But precisely the properties of the Hbac-Lewandowski representation that we use in loop quantum gravity save the day and give us, again, quantum mechanical commutation relations and self-adjointness of this thing. So now we are already very far, because now, because of representation theory, we know a lot about what can happen. The only question left to answer is, will it happen? i.e., will we get the, for example, the spins for a total spin that we expect? You know, does the how does this work? Do we get all the spectral values that we expect? And we can take a simple example where we just take two fermions here, I'll try to do this with the laser pointer here. We transport them to a common point, we add them, and then we look at the length of this thing. And then the question is, can we find eigenstates of this? And indeed, that's not so hard to do. Just put two fermions at the points where this thing measures the fermions, connect them with the spin 1/2 line along the transport line here, and calculate, and then you find, yes, that's an eigenstate, and it's an eigenstate to eigenvalue 0, so it's a singlet state of two fermions. So that's the simplest kind of combo that you can build, and it behaves kind of like expected. You can generalize this by letting a spin J holonomy run through the whole thing, but you couple the fermions such that at the end, when it runs out, you end up with the same spin, and then maybe not too surprisingly, you again get a singlet. Is there also a triplet state? Yes, there is, and it's really very suggestive how this works. So you can couple the second fermion in such a way that it increases the spin by one more notch, and then you calculate, and you find indeed there's a triplet state. It's a little funny because triplet implies that there are three states, but if we wanted to have these three states, we would somehow have to look at the gauge invariant states, gauge non-invariant states. Maybe they are there, but those are unphysical. Yeah, we don't know what we're doing there. So here we just have to contend with one triplet state, one gauge invariant triplet state. How does this generalize when we have multiple fermions and more general states, more general spin networks, and so on? That's not entirely easy problem, because the spin, for obviously the spin operators and the gauge transformations don't commute. And in fact, so this gauge invariant space lies kind of in a weird way inside the irreps of the these spin algebras, and so one has to do a bit of work. But we have found some algorithm how to create many eigenstates, and we start again by putting the fermions in the places where this thing measures the spins, and we put an arbitrary, we couple them to an arbitrary spin network, can be anything. And then we modify this spin network that we started with. And I don't know if one can read it. I've tried to indicate it here. So what we do is we sort of we reroute the spin going out of the fermions to the common point, and then from this common point back out along the lines that are in the definition of this total spin here. And so this is in fact not a spin network, because we are going back and forth here, but this is a linear combination of spin networks. And yeah, but in any case, at this common point here, we have to put an intertwiner. And then if I draw you this blown up here, then you see the intertwiners are basically just permutations and of these spin 1/2s that go in and out. And so that means we have an action of the symmetric group on this intertwiner space, and that action commutes with the total spin, and we can then the irreducible representation of the symmetric group are then the eigenstates of this total spin squared. And in this way, indeed, we can show that for n spins, we get exactly the expected spectrum of the total spin. We can construct states with any spin between 0 and n½ And there's also some interesting results about the multiplicity of these states. I mean, anyway, there are diffeomorphisms, so the multiplicity technically is infinite, but in any case, there's a different multiplicity, and one should check whether this also works out with expectations in a sense. One can do more. One doesn't just have to consider the spin squared. One can, for example, consider component of one spin in the direction of another spin, or one can consider the component of a spin in the direction of a normal to a surface. Those are well-defined operators one can write down, one can analyze. So quantum geometry is a little bit richer with these fermions. And when one plays around with this, one notices that spin and area also have a relationship, although it is not always extremely direct. Aligning spins can increase area. I've given you a simple example here where we put a lot of fermions in a box, and well, on the one hand, we can put them in a state such that their spins add to 0, or we can put them in a state where the spins add, basically. And then you see in this particular configuration where we use these linear states, then indeed we get an increase in area of the box, if you like, and also the geometry changes. Now that at first sounds very exciting, because you could think like in a solid we have lots of spins and then we can easily align them.
Sorry, Hanno,
maybe yes,
there is around 2 minutes left.
Okay, thank you. I'm almost done.
Okay.
So you could get excited, but the effect is very small, because when you analyze it properly, it's L Planck squared, and so unless maybe there's circumstances where you do something smart, it's going to be never measurable. And also, it's not clear right now whether this is universal at all, or if this is just depending a lot on the special circumstances. Finally, I want to point out to you that that sort of the spin in these spin networks can sometimes be interpreted as angular momentum. Is not something entirely new. People have pointed this out before. Krasnov has made some argument for black holes that was very heuristic, but he got a nice inequality that one can interpret in classical terms. Boyovald did the same, did something very similar, but for asymptotically flat situations, or rotation in an asymptotically flat universe, has something to do with the spins running out to infinity. And the most detailed work is by Fraudenperez, Panzetti, and Roken on rotating black holes. And there one can envision the rotation of the black hole as some sort of special edge with a very high spin that runs into the black hole. I mean, this is, yeah. So that is nice. To summarize, fermions and in-loop quantum gravity are exciting. We can work with their spin. It seems to work exactly as we expected, which is a good thing, probably. And yeah, more things can be done, especially one can look at these observables more. This area effect of spin should be characterized better. It would be nice to make this relation to the spinning black holes more precise, maybe align the fermion spin and then drop them into a black hole, or make a black hole out of them. Yeah, there's some math physics thing that you can ask me about Doppler-Haag-Roberts charges and open ends and loop quantum gravity. And well, maybe these open ends by themselves can be made to make sense somehow. So, and now I really went over time, I'm sorry, but I stop here. Thank you for listening.
Thank you. Thank you for your talk. Are there any questions? Oh, yes, I see. Jurek?
I would like to comment on this relation between spin and area. So, given a closed surface that intersects a spin network, the spins in coming to the surface have to, or intersecting the surface, they have to satisfy some identity. And then this identity depends on whether spin network is just gauge invariant, or if there is or if it's not gauge invariant, it means it contains some spin inside. So this effect, well, is known from geometric point of view without having spinor fields. It's just known from dealing with closed versus open spin networks and closed surfaces. And it also depends on topology of space-time. So it may be that this closed surface has interior, well defined, it divides space-time into space into two disconnected pieces, but it also may be as if we are in three-dimensional torus, for example, and then this closed surface may not have interior, because it may be that if we go around, so then those identities slightly differ, and for this reason they may give different result for area. But I think that, as I agree with Hanno, with you, that this result is always very small. I think it doesn't accumulate. So if we put more spin, we don't have bigger result. It's just, I think it's this identity is between something integer or half integer. So sometimes some spins have to add to some integer, and some other time they have to add to half integer, no matter how much spin is inside. As far as I remember.
Thank you very much, Jurek. That's a great comment. I am vaguely aware of this, and we should look at this again carefully, because you are absolutely right. From the view of the spin network, whether there are fermions or not doesn't matter. It just matters whether it's gauge invariant or not. So that's a good point. However, my argument somehow here, or my hope, is that there's something more. So in these examples that I showed you, it's really adding. So somehow the when you align the spins, then really you get much more, like, proportional to the number of fermions. So it might be related. Maybe it is the same. I don't know. I have to look at it. It's very good. Very nice point. And it's also that what you say is like a very elementary fact about loop quantum gravity that is somehow probably pretty robust.
Okay, thank you. Wolfgang?
Hi, Hanno. Hello.
Hi, Wolfgang.
Perhaps a related question. So in spin forms, we have this very nice Minkowski theorem and this interpretation of spin network nodes as quantized polyhedra. But now when we couple fermions to the, so this is more like a comment, not so much a question. But now when we couple fermions to the spin network nodes, what we essentially get is like a small additional phase in the effect that is not geometric. That
so some defect in a sense.
Yes, and yeah, could one envision now some similar? So when you look just at one area, but rather not looking at one area, but rather how this polyhedra then glue, and how there is some sort of defect or failure or some sort of holes that prevent perfect gluing or something like that.
It's a pleasure to be here with you guys. It's very nice, a very nice idea. I also thought that, ultimately spin is something non-covariant. It would be nice to do something in a covariant setting, and this would be a very nice project to look at this. That somehow also the fermions in spin forms, that they carry a little bit of area or a little bit of curvature. I don't know what it will turn out to be, that they carry this with them, and that this gives some interesting effect. Very good. Very good.
Or relating it to, because they are also they're a source of torsion depending on the coupling.
Yeah, they're a source of torsion. Absolutely.
And
yes.
There's this long thought that perhaps torsion is related to failure of geometricity or failure of closure or in a polyhedron. Okay, thanks.
Thank you. Very nice.
Thank you. Thank you. Thank you, Hanno, for your very nice talk. And let me now introduce the next speaker. Could you stop sharing?
Yes. Yes, I hope I did.
Yes, perfect. Our next speaker is Robert Zager, and he will talk about revisiting loop quantum gravity with self-dual variables.
Thank you, Martin, for the kind introduction. Thank you all for being here. And I want to also thank the organizers of this session for the opportunity to give this talk here. As you already heard, this is some joint work together with Hanno Salman. So the start of loop quantum gravity was when Ashtekar formulated GR in terms of his self-dual variables, which are an SL to C connection, which is the pullback of the self-dual part of some space-time Lorentz connection, and the corresponding densitized triad, which is the pullback of the self-dual part of this wedge product of frame fields. Some connection is called self-dual when it's an eigenvector of the Hodge dual with eigenvector with eigenvalue plus or minus 1 for self-dual and anti-self-dual. So already here you see that we have to work with complex variables because this I shows up here. This procedure is unique for space-time dimensions, and also Hanno just mentioned this chiral fermions coupled to the self-dual or anti-self-dual part of this connection. Loop quantum gravity, the theory that is known today, is not based on these variables, but on the real Ashtekar-Barbero variables, which are an SU2 connection that consists of the Christoffel connection and the extrinsic curvature, and they are related by the real Barbero emission parameter and some corresponding electric field. What are benefits that are expected for some theoretical self-dual loop quantum gravity? At first, when you look at dynamics, only the Euclidean part of the Hamilton constraint shows up and not the Lorentzian part. It fixes the ambiguity in the emission parameter as we fix beta to be plus minus 1, sorry. And from the application to black holes, one expects that self-dual variables reproduce the Bekenstein-Hawking entropy without having to adjust the emission parameter. And as we'll hear in the next talk by Konstantin, they also play an important role in supergravity because the generalization of Ashtekar's variables have some very special properties here. So why is LQG today not based on these self-dual variables, but on the real ones? The two main obstructions are that one has to impose reality conditions to get from this gravity description in complex variables to a quantum theory for real gravity, so to say. And then these reality conditions one imposes, this is basically reality of the geometry. So one wants the spatial metric to be real and one wants to stay it real, and then it stays real under time evolution. The other big problem when constructing a Hilbert space is the non-compactness of SL to C. Let me briefly give you an overview of some literature. There were, of course, the fundamental works and ideas in the mid-80s to late 80s by mostly these number of people there. However, it was not possible to quantize the self-gravity in these self-dual variables, except for some model systems like spherical symmetry and in some cosmological context. They played an important role in all the work of Wick rotations, Coherent state transform, and complexifiers in the 1990s, where these people were involved. And maybe most recently, Wieland used these self-dual variables to describe real gravity and basically find loop quantum gravity again. What we are interested in is really just going back to this origin, so to say, of loop quantum gravity and see what we can understand about this old problem with the viewpoint basically 30 years later. Because it was, at least for us, quite confusing to dig through the literature and get all the information together, I will try to give some rather detailed review on general relativity based on a complexified Lorentz connection, where we will single out its self-dual part and then talk about what are these reality conditions, how can one formulate them, what are the consequences of this. And after that, I will try to sketch the first steps towards some quantum theory based on these self-dual variables, and at least can show you how to implement the reality of the spatial metric. So let us start with the Palatini action with respect to some complex Lorentz connection, or connection of the complexified Lorentz algebra, omega here, which is complex. Then this action consists of complex frame fields and the corresponding curvature. And one can split the complexified Lorentz algebra into a self-dual and an anti-self-dual copy of SO31 using such orthogonal projectors. The action splits in parts as pluses minus, which then on their own just depend on self-dual or anti-self-dual objects. When one would do this for the real Palatini action, such a split, one would get these self-dual, anti-self-dual objects, and complex conjugation would just map between self-dual and anti-self-dual objects. And the real Palatini action can be expressed as basically the real part of this self-dual action. This identification, or this relation between S plus and S minus here is not the case. They really have to be treated independently. Before we do this, let us go over from SO31 to SL2C, where we can use these projectors again and define SL2C spin connections A plus minus. Singling out the plus part means just forgetting about the S minus action. We rewrite the action in terms of these now SL2C variables, and also will, for notation reasons, just drop the plus. The rest is just choose a real foliation. This defines then a complex spatial metric and perform the Legendre transformation. We will come to the Hamiltonian density in a second, but first let us look at the canonical pair we can read off here. So the canonically conjugate variable to A is this E that depends on sigma. So it has a lot of information about the tetrads in it. And naively, one can read off from this the Poisson relation. And what one reads off is just the Poisson relation for these complex variables A and E. And there is an additional factor of I compared to the usual Poisson brackets. And this, in fact, causes some problem, or at least some confusion, because one now might ask, what about the real and imaginary parts of our variables A and E? Do we get a complex structure or Poisson relations for them? From this piece of the action, we can read off the symplectic structure, omega, which is when we suppress all the indices just of this standard form. And then we can take A and E and expand this in terms of real and imaginary parts, like this, and read off a similar omega. The problem now is that this is not invertible for some Poisson brackets. So starting with this Palatini action with these complex variables, we do not get some theory for the real and imaginary parts of our variables. So this really has to be seen as some holomorphic action in the holomorphic variables A and E. This is, for example, different in what Wolfgang did, where he specifically constructed the phase space in such a way that he can deal with real and imaginary parts. So let us look at the constraints. One gets just the what is for the Hamiltonian constraint, just this part, which is called the Euclidean Hamiltonian constraint, where one in the real theory expects two parts, the Euclidean and the Lorentzian. And the name just comes from the fact that this exactly looks like the Hamilton constraint for Euclidean gravity. So this might, because there's a term missing, simplify the dynamics in some sense. One gets a diffeomorphism constraint, which is just the usual constraint, and also a Gauss constraint, which now instead of SU2 gauge transformation generates SU2C gauge transformations. What one might ask now is, what about triads in the self-dual formulation? Because in the real formulation, imposing time gauge restricts tetrads to triads, which then are the canonically conjugate to the SU2 connection there. Here in this setup, time gauge is not possible. It's just compatible with self-duality, but this really does not cause any problem. But we can look at such a contraction of two of these E's, which is in fact a complicated contraction of two of these sigmas, but in the end, just turns out to be the densitized spatial metric. So in this sense, the E's are really frame fields or densitized triads, with the big difference compared to the time-gauged SU2 theory, that because of this involvement of sigma here, we have components E0 in E, so this really are not purely spatial quantities, but know about space-time, so to say. So let us talk about the reality condition, reality of the metric, and reality of Q dot, which is the derivative of Q with respect to the Hamiltonian here. And one can now ask, why are they called conditions and not constraints? We just saw there's no real symplectic structure. And if we look again at the Poisson bracket, one really has to understand this as a holomorphic Poisson bracket with respect to holomorphic functional derivatives that just don't see E bar and A bar, which would appear here on the right-hand side. So these conditions cannot be seen by the Poisson bracket. And another consequence of this holomorphic Poisson bracket is that our phase space has to consist of holomorphic functions of A and E. As we just saw, all the constraints do not involve any complex conjugation, so they are also holomorphic. And the reality condition just cannot be treated in Dirac's algorithm as constraints. So the only thing that is left with them is try to impose them later in the quantum theory. We now can formulate these conditions in terms of the variables A and E. And it turns out that the reality of the metric is equivalent to the positive definiteness of the densitized metric. If we would have just reality here, this would allow for purely imaginary metrics. And this is also equivalent to E being real modulo gauge rotations, which means that E is real and any imaginary part can be removed by rotation. This result can also be found in the most recent literature by Ashtika and Baradarian, which is a beautiful review of this, and where we adopted this notation of real modulo gauge rotations here. For a similar statement for the second reality condition, we have to look at the covariant derivative that is compatible with E, which we call curly D. And this leads to some connection in terms of E. And we can look at the difference of these derivatives or connections, which we call K. And then a similar statement is that the reality of Q dot is equivalent to the reality of the derivative with respect to some Hamilton constraint, where we have to choose some laps of the densitized metric, or that K is real modulo gauge rotations. It's now possible to just take two of these conditions and combine them to a set of reality conditions. And most prominently in the literature, you find 2 and 2 and 3 and 3. So this concludes basically the end of the review part of this talk. And for the rest, I will just focus on the first reality condition in some quantum theory setup. While I can only say that we are working on the second reality condition, but there is really just no robust statement I could give here. So let us look for a second at the role of these gauge rotations here. If E would be real, if this would be our reality condition, then this gamma of E would be a real function. The second reality condition tells us that K is real, and as a consequence, the connection would neatly split into this real gamma plus I real K, which somewhat exactly looks like the real Ashtika-Barbero connection with Barbero immutable parameter equals to I. If we allow for these gauge rotations, then both E and K are real modular gauge rotations. Both E and K have some imaginary part, which then mix in the real and imaginary part of our connection A. So these are both complex SL2C connections. One could work with both of them. Here they are just neatly separated in this gamma and K part, real and imaginary parts. Why am I telling you this? What we want to do is to choose some gauge fixing to get rid of these gauge rotations. So we want to look at a reality condition that says E is real. Why are we doing this? Because we want to quantize basically E just in the usual way without these gauge rotations, and then transfer the reality of E as a self-adjointness or adjointness relations of the corresponding flux operators. Before we go to the quantum theory, let us have a look at the algebra of holonomies and fluxes. Holonomies are now SL2C valued. They have the usual properties under concatenation inversion. We can define fluxes in the usual way, just the Hodge star of E smeared with some function and integrated over the surface. And from the Poisson relation, we get a canonical commutation relation, which really just looks like the standard case for SU2, with here SL2C holonomies, of course, with an additional factor of I. And this motivated us to look at holomorphic invariant vector fields of SL2C, where we have left-right invariant vector fields with respect to the basis of SL2C, or the generators of SL2C, which are, of course, the generators of SU2, but now with some complex parameters, and we take the holomorphic derivative here. So we can express the CCR really in terms of invariant vector fields here. What is interesting about this is we, in the beginning, had three holomorphic components E, which we have to work with, and we were able to match these with three pairs of holomorphic invariant vector fields. Or if you want to see like this, we took the holomorphic derivatives I showed you for the Poisson relation and transferred them to holomorphic invariant vector fields in the commutator. As we are working on some holomorphic phase space, there cannot be the sensible notion of complex conjugate and therefore of adjoint, for example, for the holonomies. So this algebra cannot be a C-star algebra, at least at this point. We do not get the usual Ashtika-Lewandowski representation via the GNS construction, and the Loss-Fleischak uniqueness result for this representation cannot apply. So at the moment, this really looks like we are quite far away from the usual holonomy flux algebra for the SU2 theory. So now for the quantum theory, you have the classical holomorphic theory, and the idea is to take this holomorphicity over to the quantum theory. And there we, as suggested in the literature from early on, try to implement the reality conditions as via a choice of inner product. The simplest choice we could come up with is a Hilbert space of holomorphic square integrable functions of SL2C. So we're just looking at a single edge where we have the Haar measure for SL2C and some additional measure factor function mu. And we want to use the freedom in mu to implement the reality conditions, so to say, by hand. We have this as an inner product, and let me make clear what holomorphicity here means of these square integrable holomorphic functions. It means holomorphicity with respect to the components of the group element. And since these psi or phi then are analytic functions because of the holomorphicity, psi bar are anti-holomorphic automatically. What would happen if we would not make this holomorphic ansatz? We have only the commutators of the complex or holomorphic variables fixed by the Poisson relations. So any other commutators, like for real and imaginary parts of E and A in the quantum theory, would be highly depending on the choice of representation. And to keep this as simple as possible, we disregard these commutators and try to see this holomorphic Hilbert space as a minimalist ansatz for the quantum theory. So what about the first reality condition? We take E, we want it to be real, quantize it in the usual way. We quantize the fluxes as the commutators. Let me again stress that this smearing function here is now really SL2C valued and complex. So self-adjointness of these fluxes does not really make sense here, but we want to implement the reality condition as an adjointness relation in the sense that it is basically self-adjoint up to complex conjugation in this smearing function. And this, in fact, can be accomplished by the self-adjointness or by demanding self-adjointness of these holomorphic invariant vector fields. So let us take the inner product, act right, act left, for example, with the left invariant vector field. We take this action in both cases and transfer this to an action on this measure factor, and therefore can read off conditions for the left and right invariant vector fields, where now these L and R bar mean the anti-holomorphic invariant vector fields. We can solve this by setting mu of GG bar a function of the trace of GG dagger. This is definitely a sufficient condition. At this point, we are not really sure if this is also necessary, but what one sees here is the immediate effect of the gauge fixing in the reality condition we did. So GG dagger is, of course, only invariant under SU2 gauge transformations and not anymore under SL2C gauge transformations. But with this solution for the first reality condition, there's still enough freedom in this mu left to tackle the non-compactness of SL2C. If one just in a brute force way choose some Gaussian function of the trace of GG dagger, we would be left with the first reality condition solved and some finite inner products. So for my last point, let me introduce the idea of holomorphic spin network functions.
I'm sorry, you have 3 minutes. Sorry,
yeah, that's fine, thanks. By its unitary trick, we know that every irreducible representation of SU2 is a holomorphic irreducible representation of SL2C. So just the usual SL2C matrix elements now, usual representation matrix is now with an SL2C argument. These, in terms of the representation theory of SL2C, are the J, 0 part of the finite dimensional representations. The 0J part would correspond to the anti-holomorphic irreducible representations. And just as a comment, we are not using the unitary irreducible representations because we want to build some holomorphic Hilbert space, and these unitary irreps are just not holomorphic, so we cannot use them. So now the holomorphicity comes again into play because these psi of G are analytic functions of the components of the group element. So we can express them in terms of the representation matrices. And in fact, it turns out that from the first reality condition, we see that the representations, these holomorphic representations, are orthogonal, and therefore the holomorphic irreducible representations of SOTC form an orthogonal basis of our Hilbert space, where the normalization then depends on mu. And with this, one can just try to build ordinary spin network functions, or the known spin network basis now with respect to SOTC holonomies. And this close relation to the SU2 representation theory tells us that we have just the same recoupling theory for SOTC and the same interjoiner structure here for these spin networks. So the SOTC Gauss constraint can just be implemented with the usual methods. And even if one would be thrown back to the SU2 by this gauge fixing, also this constraint would be implementable. So let me briefly sum up. I hope I could clarify some details about complex GR in self-dual Ashtikar variables, and I hope also it was clear that how these reality conditions come into play, why they're important, and that it might even be possible to write down some holomorphic quantum theory based on these variables. What I really want you to take home is that these self-dual variables from basically 30 years ago are still interesting to look at, and at least the first reality condition can be implemented, but we hope that also the second reality condition will be at some point, which leads me to what I'm currently working on. And this is really just work in progress and some ideas. The next thing is the implementation of the second reality condition. And let me just tell what we want to do is pose this as an adjointness relation for the level of spin networks, or at the level of spin networks. And after this, to get some proper Hilbert space for some self-dual loop quantum gravity, one needs cylindrical consistency. And if there's any freedom in mu left, we hope that this fixes this. And as you might have noticed, holomorphicity somehow, or this holomorphic concepts, aids quite a lot in this construction, and at least in the solution of the first reality condition. So we really want to understand what's the role of this, because what we're basically doing is take the representation theory of SOTC and throw away half of it, by just considering the J,0 part. And I think this is all I wanted to say. So thank you.
Thank you. Thank you for your talk. We have a time for one question. Jurek?
So what about conjugate to the holonomy? It seems to be creating anti-holomorphic functions.
Yeah, that's the problem. And at the moment, we just do not know what, because this measure mu is not fixed, we do not really know what the adjoint of holonomies will be at the end. So this is what we really don't understand about this at the point.
The adjoint exists. It depends on the measure, and if it's densely defined or something like this, we cannot yet tell. It's an important point. Yeah. This will be the second reality condition will have a say there.
Okay.
Can I maybe ask a quick question?
Okay.
So so if you do quantization of QED, for instance, and do it covariantly, then we start out with a Hilbert space or with a space which is equipped with an inner product, but which is not positive definite. Like there are creation and annihilation operators that carry space-time index mu, and A dagger mu A is like eta mu nu or something. And couldn't we do something here too, that we work with holomorphic functions all the way, and instead of looking for a Hilbert space, we just work with the space with inner product which is not positive definite, then forget about reality conditions altogether and just try to quantize the constraints on this inner product space. Wouldn't that be something to consider, or?
I guess it could be. I don't see anything that speaks against this, but we just haven't considered this at this point because we just wanted to start with this holomorphic quantum theory, but it's definitely interesting. Yeah.
Maybe maybe we discuss privately.
Yeah. Thank you.
Okay. Thank you. Thank you again for the very nice talk. And let me now go to our next speaker, Konstantin Eder. He will talk about supergravity in loop quantum gravity. I'm sorry, you're muted. Konstantin?
Now, can you hear me?
Yes, I can hear you.
So sorry. So thank you to the organizers for the opportunity to present my work, which has been done in joint collaboration with Hanno Salman, and which is about various aspects of supergravity and loop quantum gravity, and the results you can find in the paper. Now, in my opinion, this is in fact a very interesting topic to study. As supersymmetry, it's a unified description of bosonic and fermionic particle species, and thus may shed a lot of insights of how to treat them in loop quantum gravity. And in particular, we will see that supergravity has a lot of interesting geometrical structures, which may also have interesting applications in loop quantum gravity. I cannot move. Okay. Okay, but before I start with the main part of my talk, let me briefly introduce some basic facts of supersymmetry and the present status of supersymmetry in loop quantum gravity. Now, in quantum field theory, one has this famous Mandela-Kalomanda theorem, which states that the most general Lie algebra of symmetries of the S matrix given by the direct sum of the space-time symmetries, so the Poincare algebra and the Lie algebra of internal symmetries, which could be, for instance, gauge symmetries, and in particular, this is a direct sum, so there's no mixture between space-time symmetries and internal symmetries. And it was found, so if one would like to go around this, it follows that one needs to introduce some new kind of algebra, and this was the result of Hartlub, Jansky, and Sonius. We found that this can be circumvented if one considers so-called super algebras. So these are the two-graded algebras consisting of algebra G, which decomposes into an even part, G0, called the bosonic part, and some odd part G1, which is called the fermionic part, and some additional commutator, which restricts to the standard commutator on the G0 and the anti-commutator on G1. And then we can study the smallest possible super algebra which contains the spacetime symmetries. In that case, one finds that this is given by the super Poincare algebra or super anti-de Sitter algebra in case of a non-vanishing cosmological constant. And this algebra in both cases splits in this form with G0, the even part given by the Poincare algebra, generated by spacetime translations and Lorentz transformations, and some odd part which is generated by a fermionic generator Q alpha, which is a Majorana spinor. And this then again satisfies these additional commutation relations. And in case of a non-vanishing cosmological constant, this requires additional contributions, which are proportional to some length scale L, which is the so-called anti-de Sitter radius. And also can include further generators to the theory, fermionic generators in the theory. In that case, if you have n fermionic generators, you call this an n-extended supersymmetry. Now, supersymmetry in Lqg has been discussed already in various references. For instance, the reformulation of supergravity in terms of Ashtiger variables has been first considered by Jacobson, then Philip, Cambini, Obregon, and Pullin, and also Ling and Smolin. Also, the quantization of the theory has been considered by Ling and Smolin in the early works, and later on for real variables by Bodendorfer, Thiemann, and Thurn. And finally, also spin-form models in D equals 3 have been considered mainly by Levin and collaborators. Now, as it turns out, the canonical treatment of supergravity theories generically suffer from very complicated constraints. So in the canonical theory, it follows that supersymmetry is completely hidden in the formalism. So when I then ask the question, is there a possibility to treat this canonical theories such that at least some part of the underlying supersymmetry is still manifest also in the canonical theory? And this is in fact the main, so the core of this talk. So we would like to discuss this question, how to reformulate the theory in a way such that at least some part of the supersymmetry is still manifest in a canonical theory. And therefore, in this talk, I would like to talk about the classical theory, and I will talk about the interpretation of supergravity in terms of Cartan geometry. Then I will discuss the derivation of the Hausmann-McDonald-Mansui action for supergravity for arbitrary Barbieri-Misi parameters for both n=1, also in the n=2 extended case. In that context, I will talk about the boundary theory because this turns out to be very special, and it also may have very interesting applications to supersymmetric black holes. And finally, I point out particularities of the self-dual theory, and also briefly about the quantum theory, so coordinate connections, anonymies, and group integrations theory. And I actually don't have time for this, but I just want to say we have also applied this in a symmetry-reduced setting, and this can be used to study cosmological implications in loop quantum cosmology. But before I start with supergravity, let me review the interpretation of gravity in terms of Cartan geometry, because this turns out to be essential. Now, the idea of Cartan geometry is based on the idea of Felix Klein in his Erlang program, who studied the classification of geometry of space by the Erlang group of symmetries. So, for instance, you can take a Minkowski spacetime and then the isometry group, which is given by the Poincaré group. And then if you fix some spacetime event M, you see, then the subgroup of isometries which resolve this point is given by the Lorentz group. Then if you take the coset space, you see that this is diffeomorphic to the Minkowski spacetime again. So you can equivalently describe Minkowski spacetime in terms of the underlying symmetry groups. And so this leads to the definition of a Klein geometry. One defines a Klein geometry in terms of a pair GH, where G is a Lie group and H is a closed subgroup, with the additional technical requirement that the coset space is connected. Now, with this observation that flat spacetime is the equivalent description in terms of Klein geometry, Cartan formulated a theory which is now known as Cartan geometry, which can be regarded as a deformed version of flat Klein geometry, just as gravity is a deformed version of flat Minkowski spacetime. And this is the basic definition. So a Cartan geometry is modeled on a Klein geometry GH, and defined in terms of a principal H bundle, together with a one form A, defined on this bundle P, and taking values in the algebra in the Klein geometry. And this is called the Cartan connection, and it satisfies certain properties. And in particular, it leads to a local identification of the tangent spaces of the bundle to the tangent spaces of the Lie group. So the Cartan connections encode in a certain way the degree of deformation of the Cartan geometry from the flat model. And then one can apply this to the context of gravity. Someone describes gravity in terms of Cartan geometry here in case are modeled over and the zeta space given by the isometry group and the Lorentz subgroup as a stabilizer. And then we can take the Cartan connection and split it by projecting on the translational part, which gives then the soldering form E, or also called coframe, and also onto the Lorentzian part, which gives a gauge connection omega, so a Lorentz connection. And then using this connection, one can formulate an action principle. And in context of loop quantum gravity, I also want to include the possibility of finite Barbieri-Misi parameter and the derivation of the host action via using this interpretation of gravity in terms of Cartan geometry is based on the works of Andono and Derek Weiss, and in context of PF theory by Friedel and Starodubtsev. And here, in case of ADS supergravity, I would like to derive this introducing some notion of a beta deformed inner product. So in that case, one uses the identification of the isometry D algebra with the symplectic algebra, in which case it follows that the Lorentz algebra is generated in terms of matrices of this form, so they are described in terms of gamma matrices. And then using this identification, one can define an operator on the Lorentz algebra in terms of a beta-dependent Clifford algebra element, where beta is the Barbieri-Misi parameter. And then using this operator, one can define a beta-deformed inner product on the symplectic algebra by contracting this with the invariant trace. Then one can use this beta-deformed inner product in order to formulate an action principle, which then turns out to be of Yang-Mills type, with R the curvature of the Cartan connection contracted with this beta-deformed inner product. And then expanding this action, one finds that this leads to the standard host action of ordinary first-order Einstein gravity with a non-trivial cosmological constant plus additional boundary terms. Okay, now with these preparations, we then go over to supergravity, and I also wanted to discuss in this context the boundary theory and framework of loop quantum gravity. Now it turns out that using this interpretation of gravity in terms of Euclidean geometry, that one can derive supergravity by just moving everything to the super category. So we can now describe ADS supergravity in terms of super Euclidean geometry, which is modeled on a super ADS space. And again, we have a super Euclidean connection, which now takes values in the super under de Sitter algebra. And then we can decompose it by projecting on the even part, which then gives the soldering form E and the spin connection omega. And also we can project it on the odd part, which now gives a new field psi, which turns out to be a spin 3/2 field, so-called spinor field, so-called a Rita-Schwinger field. So in the supersymmetric context, it follows that the Euclidean geometry induces a connection which contains both bosonic and fermionic degrees of freedom. And then again, one can formulate an action principle, which again would like to do in terms of a particular kind of a host projection. And in fact, this turns out to be a natural extension of the host action one has in standard first-order Einstein gravity. And there one can use the observation that the odd part of the super algebra naturally defines a Clifford module. So one can naturally extend this p beta operator to an operator on the whole super algebra again by just adding an additional copy of this operator. Then one gets an operator bold p beta on the super algebra, which then can be used in order to introduce an inner product, some beta deformed inner product by contracting it with now the invariant called so-called super trace. And then using this beta deformed inner product, one can formulate an action principle, which is again of Yang-Mills type, with R the curvature of the super Euclidean connection and contracting with the beta deformed inner product. And then one finds that this leads, in fact, the host action of d equal 4 n equal 1 ADS supergravity plus some additional boundary terms. And now these boundary terms turn out to have very interesting properties. Now, because one may ask the question, what is special about the boundary terms which are contained in the superhost McDowell-Mansui action? And therefore, one may first write down the most general possible ansatz of the boundary theory, which is compatible with the symmetries of the Hbac-Lagrangian. In that case, one finds that the most general ansatz turns out to be a linear combination of 4 individual terms, where these C's are arbitrary constant coefficients. And the first term is the Gauss-Bonnet term, the second one the Pontryagin term, and the last two terms are tautological terms depending on the fermionic degrees of freedom. And then having written down this general ansatz, one then asks the question, by adding this boundary Lagrangian to the Hbac theory, that the full theory is still invariant under supersymmetry transformations. And in particular, one imposes the condition that supersymmetry is also preserved at the boundary, because this turns out to be an important question in order to deal with supersymmetric black holes, for instance. And this idea has been studied by Adrianopoli and Aurea in 2014, and then has been developed even further in a series of papers. Actually, I don't have time to explain this in detail now, but just want to say that you can study this question rigorously in the so-called Castellani-Torrier-Frey approach to supergravity using this Cartan geometric interpretation. And then one finds that imposing SUSY invariance at the boundary yields to some boundary condition for the full action. And then by studying this condition, one finds that this in fact uniquely fixes you the coefficients contained in this linear combination. So this implies that imposing supersymmetry invariance at the boundary uniquely fixes you the boundary theory. And we then have applied this to the context of host supergravity. In that case, one ends up with this unique boundary term. And interestingly, this exactly reproduces the boundary term one obtains from the superhost McDowell-Mansui action. So to summarize, imposing SUSY invariance at the boundary uniquely fixes the boundary theory. In case of host supergravity, exactly reproduces the boundary term one obtains from the superhost McDowell-Mansui action. One may then ask the question, can this also be generalized to the case of extended supersymmetry? And the answer is yes, and we have considered the n equal 2 case. And in that case, the super-Cartan connection now induces an additional U1 gauge field, which is also called the graviphoton field. And again, one can make the most general possible ansatz for the boundary theory, compatible with local supersymmetry, and in that case, it follows again, the boundary theory is fixed uniquely, posing SUSY invariance at the boundary, and as a consequence, the full theory acquires the structure of a McDowell-Mansui type action. And this was, for the case of standard supergravity, this was observed by Adrianopoli et al. And we now have extended this to the possibility of a finite Barbera-Misi parameter. And in that case, it follows that n equal 2 host supergravity again has the structure of a Yang-Mills type action. We now P beta is an operator defined on super Lie algebra value 2 forms. And this is actually due to the fact that this operator now in the U1 sector acquires an additional contribution, which explicitly depends now on the Hodge star operator. And interestingly, this term now explicitly yields a U1, a theta topological term in the U1 sector, which is proportional to the Barbero-Misi parameter. So in this setting, it follows that the Barbero-Misi parameter literally has the interpretation in terms of a theta ambiguity. Now, so far, I have discussed this in a generic setting for arbitrary Barbero-Misi parameters, but now I would like to go over to the chiral limit of the theory so beta is purely imaginary now. But in this context, it is interesting to observe that generically, if this operator p beta in the n=1 and also in n=2 case does not commute with local gauge transformations corresponding to the whole supersymmetry algebra. So actually, this theory is not a proper Yang-Mills gauge theory. But now this turns out to change drastically if beta acquires the values beta minus I or plus I. Because in that case, this operator P now becomes a true projection operator onto a proper subsuper algebra of the super and the de Sitter algebra, given by the so-called autosymplectic algebra OSP. And then using this observation that P now is a true projection operator, it follows that the superhost McDonald-Mansui action in this limit now is manifestly invariant under enlarged gauge symmetry. So one has some manifestly OSP gauge symmetry in the theory. And something similar occurs also in the n=2 case. So it follows in the chiral theory that some part of the supersymmetry becomes now a true gauge symmetry, which is some interesting phenomenon occurring in the chiral theory. And then one can use this operator and apply this on the Cartan connection, and then one gets a new connection, which one may refer to the super Ashtek connection, which contains the bosonic self-dual Ashtek connection as discussed by Robert previously, and some additional fermionic contributions. And then using this connection, one can finds that one can split this action, the superhost McDonald-Mansui action for the n=1 and also n=2 extended case. In both cases, one then finds this form. So the bulk, one finds some chiral Palatini type action with E, the superelectric field, which together with A plus builds up some gradient symplectic phase space, just a complete analogy to the classical theory, and some additional boundary contributions, which as I've explained previously, turns out to be uniquely fixed if one requires SUSY invariance at the boundary. And in context of the chiral theory, this turns out to be equivalent to a Chern-Simons theory. So one obtains a super Chern-Simons theory with OSP gauge group and some complex Chern-Simons level K. And also one obtains boundary conditions. And again, this is a complete analogy to the classical theory. So this which leads by a coupling between bulk and boundary degrees of freedom. And this leads to a coupling between the curvature of the connection on the boundary to their superelectric field in the bulk. So A plus seems to be a very natural candidate to quantize supergravity in the framework of loop quantum gravity. And interesting, it also exists in case of extended supersymmetry. By its very definition, it contains both gravity and matter degrees of freedom, and thus leads to a unified description of both, and also to a more fundamental way of quantizing fermions. And also interestingly, the boundary theory is completely fixed if one requires SUSY invariance at the boundary. And in case of the chiral theory, is described in terms of a super Chern-Simons theory. And so this turns out to be a natural candidate if one would like to study inner boundaries in the context of IQG, and for instance, study supersymmetric black holes and thus draw conclusions about relationships in treating boundary theories in context of superstring theory. Now, just very briefly, how do we formulate the theory using standard tools from loop quantum gravity? Now, therefore, we need holonomies, which are associated to paratransport maps induced by this connection A+, which we then can use in order to construct Hilbert spaces. And then we have to would like to construct a suitable basis in terms of spinetaric states. Now, as far as the holonomies are concerned, induced by this super Ashtek connection A+, actually turns out that for this construction, one encounters various difficulties in consistently incorporate the undercommutative nature of fermionic fields, which turns out to be crucial in the context of supergravity. But in fact, one can resolve this if one includes the so-called additional parametrizing supermanifold S. So in this framework, it follows that these holonomies induced by A+ now depend on some additional parameterization supermanifold S, which is needed in order to resolve the fermionic degrees of freedom in the theory. And I don't have time to explain this. It's actually a bit involved and also mathematically demanding. But I just want to say that this works out very nicely and also interestingly shares many properties. So the resulting theory shares many properties one encounters in the standard quantization scheme of fermions and Lqg gravity. So among other things, so the configuration space consisting of these generalized connections one usually considers in AQG, now besides the graph gamma, depends on some additional parameterizing supermanifold S. And now in standard AQG, since this graph gamma is chosen a priori arbitrarily, one has to ensure that the theory is consistent if one restricts to subgraphs gamma, for instance. And now the same occurs also for the parameterization. The parameterization is chosen arbitrarily. One has to require consistency by changing the parameterization. And it turns out that both operations do commute, and one gets these commutative diagrams. And this, in fact, is a crucial property because then it identifies these configuration spaces in terms of so-called Molotov-Sachs type supermanifolds. And this then can be used in order to study cylindrical functions on these bases and also invariant measures in order to construct Hilbert spaces. And one finds that for the fermionic degree of freedom, this measure, because we acquire invariant covariance under reparameterization, this induces some Vertices type integral for the fermionic degree of freedom. And this is in fact the standard measure one usually imposes in context of standard Lqg gravity coupled to fermions. And also if one studies Hilbert spaces, one encounters strong similarities with the standard quantization schemes of fermions and Lqg gravity. But of course, there are also various issues, and maybe the most prominent one is the solution of the reality conditions, because we are dealing with a complex theory. So we have to recover ordinary real supergravity, but it turns out that we have considered a certain model where this can be solved, so a particular symmetry-reduced model. And this model, we have explicitly used this enlarged gauge symmetry one encounters in the chiral theory. And in this model, we were able to solve these reality conditions exactly. So this at least gives us some hope that one may also able to solve this in some way in the full theory. Okay, so to summarize, we have discussed the Cartan geometric description of host supergravity in Diego 4 for arbitrary Barbier Misi parameters in both the n=1 and also n=2 extended case. We also included the boundary theory, and we found that the boundary theory is unique if one imposes Gaussian invariance at the boundary. And the chiral limit of the theory is quite special because it has the structure of a super-Young-Mills type theory with enlarged gauge symmetry given by a supergroup. And then this leads to a super Hbac connection. And then construct a theory similar to the classical theory. Also, we have also in the chiral limit, it follows that the boundary theory has the structure in terms of a super-Chern-Simons theory. Then also have discussed the chiral limit of the theory, the quantum description of the theory, and therefore we have constructed rigorously the created connections and studied structures and properties of these holonomies. And we found that the resulting state space has a very intriguing structure, which is in quite strong similarity with the standard quantization schemes one applies by quantizing fermions and AQG. And also we have studied applications in the context of symmetry-reduced models in order to study applications of supersymmetry in context of Lqg cosmology. And we also have yet dealt with several issues in this framework, most importantly, the solution of the reality conditions. In context of the symmetry-reduced model, we were able to solve these conditions exactly. And finally, at the moment, we are working on the applications of these results to the context of charged supersymmetric black holes and, for instance, entropy computations, because this may enable us to compare results of entropy computations in Lqg gravity to entropy computations in context of superstring theory. And also, we are extending the symmetry-reduced models we have considered by including further local supersymmetric matter fields and then study the dynamics of the theory and also possible cosmological implications. And finally, we're working on generalizing these results to the case of n greater than or equal to 3 extended supersymmetry. So we asked the question, again, is the boundary theory fixed unically? And if yes, does the resulting theory also have the structure of a McDowell-Manzouri type action, which one encounters for the n=1 and n=2 case? And a lot of other works. Thank you.
Thank you. Thank you for your talk. Are there any questions? I don't see any raised hands. So let me ask a question, just short technical question. So your super holonomies take values in what space? Is it a group? Is it a compact group? What kind of groups do you consider?
So, so in this chiral theory, this G is now this OSP gauge group. So the bosonic part is just the SL2C gauge group again. So it is not compact in this context. And so this, so it's actually some generalized group, but you can fix this. And so we are dealing still with a non-compact group. But you can, in fact, consider certain subgroups, so the so-called unitary orthosymplectic group, which can be regarded as the supersymmetric generalization of the SU2 group. And this group has very nice properties, so you can, in fact, implement cylindrical consistency, for instance. So in this framework, you can, so this actually works similarly to the SU2 case then.
Okay, thank you. Are there any more questions? If not, let's thank the speaker again. And we will now move to our next speaker, Tsung Zhang. He will talk about first-order quantum correction in coherent state expectation value of loop quantum gravity Hamiltonian. Oh, I see something changed. So he will talk about computing expectation value of full Lqg Hamiltonian to the next leading order. Okay.
So can you hear me?
Yes, now we can hear you.
Okay, very good. So at first, so I would like to thank the organizer and the host of our section, so that I have a chance to share my work. So this is a work in collaboration with Mu Xin and Shicong Song. So the paper has been put in archive, and the title of this is Computing Expectation Value of Full Lqg Hamiltonian to next to leading order. There is this long-term confusion that the quantum dynamics of Lqg might not be computable analytically. So because of the non-polynomial Hamiltonian constraint. But this confusion was answered by Gisu and Tiemann, so who proposed a scheme to deal with a wide class of non-polynomial operator in 2006. So with this proposal, so someone compute the expectation value of the Hamiltonian constraint under the isotropic and homogeneous coherent state to the leading order in Hbac. So in those work, the author take the full loop quantum gravity Hamiltonian and calculate its expectation value at the homogeneous and isotropic state to get this result. And at the quantum theory, so it is crucial to study the Hbac correction of Lqg. So in our work, we will focus on this term, the Hbac order term in the full Lqg framework. So this is actually first motivated by some models in LQC. So in LQC, one studied the effective Hamiltonian, which is the expectation value of the Hamiltonian operator under some coherent state. Taking advantage of this effective Hamiltonian, one just calculated the classical evolution generated by this effective Hamiltonian and get the symmetric or unsymmetric bounds depending on the model. And also when studied the quantum dynamics, it turns out that the effective dynamics and the quantum dynamics can coincide with each other very well. So motivated by these models, we are going to compute the Hbac correction of the expectation value of the full Lqg framework of the full Lqg Hamiltonian with respect to some coherent state. However, the coherent state in full Lqg is just kinematic. So we didn't know too much on the consistency between the quantum dynamics and this effect and this coherent state. So the point is that if those coherent states is preserved by the quantum dynamics or not. However, someone started this question. So currently, a new path integral formulation of loop quantum gravity was proposed by Mu Xin and Heng Guang. So they and their work relates the effective Hamiltonian and the quantum dynamics correctly. So what they did is the following. So they consider the coherent state path integral formulation of loop quantum gravity to get the effective action. And from this effective action, we can see that the expectation value of the Hamiltonian operator is involved. So according to those formulations, we can see the Hbac correction of the expectation value of the Hamiltonian constraint partially gives the dynamics some quantum correction. And what we are doing is the following. So first, consider a cubic lattice. Based on this lattice, we can introduce the T-mass coherent state picked at the homogeneous and isotropic date. And then we consider the Hamiltonian constraint operator to calculate the expectation value of this operator with respect to this coherent state, and expand the result with respect to this parameter t to the next to leading order. So this parameter t is some parameter proportional to the square of the Planck scale, the square of the Planck scale. So we get the Hbac correction of this expectation value. Because the computation is very, very complicated, so we have to use computer to do this computation. So these are the code we write to do the computation. With this code, so we can first compute the expectation value of any monomial of Holonomy and the flux. So this is just at one edge. So the Holonomy and the flux operator located at the same edge. And also with this code, we can simplify the operator with the commutators. So this means like we use the basic commutation relation between flux and the Holonomy operator to simplify the operator in which there are commutators. And the code actually has been shared online with this link. So everyone is welcomed to go to this link to use this code. And this is the result we get. So this is the result of the expectation value of the Euclidean part of the Euclidean part with yeah. So and this is the result of the I'm sorry, any question?
No, I don't think it's a question.
And this is the result of the expectation value of the Lorentzian part, so up to the order t, right? We do this computation with two 48-core processors, and the parallel computation with 96 kernels spanned about 2 weeks. So it is noticed that although the homogeneous and isotropic coherent state are considered in our work, but the code can be generalized to an arbitrary case easily. Now let us come to some details of my work. So in my work, to begin with, I would like to first introduce some basic knowledge of the T-mass coherent state. So let G be so this is the given a graph gamma. So let G be a map from this graph to SL2C group satisfying this condition. And the T-mass coherent state is given by the tensor product of SU2 coherent state at each edge. So the SU2 coherent state, this psi GE, is given by this equation. So here GE is an SL2C element. So we can do this decomposition for this SL2C element, where NS and NT are SU2 element, and this Z is just some complex number. So these three equations interpret the geometric meaning of these three parameters. For instance, so if we consider the expectation value of the flux operator located at the starting point of the edge, so its expectation value is given by the product of the real part of this complex number and a unit vector associated to the corresponding SU2 element. And the relation between these unit vectors, those vectors NS and NT, with the SU2 element is given by this equation. So, and for the Hamiltonian operator, it is usually divided into two parts. So one is called the one is the Euclidean part, and the other is the Lorentzian part. So in our work, we consider the graph preserving Hamiltonian operator. So that means for the loops involved in this two operator, we will choose the minimal loop. So for instance, this loop H alpha, this loop alpha ij will be the minimal loop containing the edge EI and EG. So what we are doing is to compute respectively the expectation value of the Euclidean Hamiltonian and the Lorentzian Hamiltonian with respect to the T-mass coherent state introduced just now, and expand the result with respect to the parameter T to the next to leading order. And a problem in our calculation is the volume operator. And we know, so in this volume operator, there is a square root. So because of the square root, it will be very hard to calculate the action of this volume operator on some spin network state. However, as far as the expectation value with respect to the T-mass coherent state is concerned, so it turns out that one can just replace this volume operator with this operator VGT. So in this expression of this operator VGT, this CK is just some constant. So we can see that this VGT is only a polynomial of a flux operator. So that with this replacement, so we can we will get we will reduce the operator to be the polynomial of flux and Holonomy, so which is computable. So for instance, for doing this replacement in the Euclidean part of the Hamiltonian operator, we only finally need to consider the expectation value of this operator. And for the Lorentzian part of this operator, we only need to consider this operator. So they are both the polynomial of flux and the Holonomy. So this page shows the complexity of the computation. So now, even though the expectation value is computable, but the complexity of this computation is actually very huge. So there are two reasons causing the complexity, the huge complexity of the computation. So the first one is the sum over indices of flux and holonomy for fixed edge and vertex. So for instance, taking the Lorentzian part as an example. So there are actually contraction of the indices in the fluxes and holonomy. So here. So let us just consider the contraction of the flux indices as an example. So by our experience, so if we only consider the leading order of the expectation value, so to calculate the expectation value of this term, so this term with respect to some specific edge and the vertex, so we need to do at least 10 to power 10 times calculation. So if one time calculation needs 1 second, so this is just like 2,000 years. So, and if the next to leading order is considered, if the next to leading order of the expectation value is considered, so so we need like 10 to power 14 times calculation. And if each one need 1 second, we need like 2 million years. So that is infinity for us. And also this is only one reason of the complexity. So the second reason of the complexity is the sum over edges and the vertices. So this summation will lead to the complexity to be 10 to power 5 times of the complexity we mentioned just now. So because there are like 10 to power 5 terms in this summation, with respect to the edges and the vertices. Of course, so we didn't need that much times because we finally get the result, and our computation with this 248 core processor finally spent like 2 weeks with 96 kernels. So this is because this is because of the following two reasons. The first, we found a theorem to judge the order of the expectation value. So taking advantage of this theorem, so we can easily exclude the cases of indices for which the expectation value are of higher order. And the second is because of our algorithm designed to avoid repeated computation. So because of these 2 points, the computation complexity decreases exponentially so that we can get the result in time. So let me just give a sketch of our computation procedure. So taking the Lorentzian part as an example. So in the expression of the Lorentzian part, there is a prefactor which is of order 1 over t to power 7. So because of this factor, so for instance, if we want to compute the expectation value of this operator up to the next to leading order directly, I mean with this expression. So that means we need to consider the expectation value of the operator part to order t to power 8, so that we will get the result to the next to leading order. So that will be a very huge work. So in order to reduce the complexity of our work, so we need to first simplify the operator. So because there are commutators inside this operator part of this expression, we just use the basic computation relation to simplify this operator to re-express this operator to be this form. So here H0 and H1 are just operators of order 1. So with this expression, so if we want to get the result up to the next leading order, we only need to consider the expectation value of this operator H0 to the next leading order. But for this operator H1, we only need to consider its expectation value to the leading order. And then we factorize this operator to expectation value on individual edges, so that on each wedge, so we just have expectation value of monomials of holonomy and fluxes, which is computable. And with our code, we can compute those expectation values efficiently. So this is the sketch of our computation procedure. And we are not going to the details of this procedure because we don't have enough time today. And this shows the result of our, shows again the result of our computation. So this is the Euclidean part, and this is the Lorentzian part. So here we consider a toy model. So a toy model to consider the dynamic, so governed by these two expectation values, and consider the effective of the expectation value. So for the first plot, so it is the evolution of the volume. It is the evolution of the volume with respect to the time t. So here we consider the model of gravity coupled to Gaussian dust, and this t is the dust time. And so from this we can see if we consider the effect of the next leading order, so there will be another bounce caused by the next to leading order expectation value. And the reason of this recollapse is that, so when Kc, so when Kc is like this Kc is proportional to this C in loop quantum gravity, in loop quantum cosmology. So when Kc goes to 0, so the next to leading part does not vanish. And so this is only from the Lorentzian part of the expectation value. So it is this term, so that causes the recollapsing of the evolution. And the distance between the two bounds, the distance between these two bounces are actually proportional to 1 over t. So that means if t goes to finish, so this recollapsing will occur at the infinity time. So here is the plot of the critical density. So that is the density at the bounce here, at the bounce and at the bounce here. So we can see, so without considering the next to leading order effect, the critical density will increase to infinity. But considering the effect of the next to leading order, so the critical density are actually finite. Okay, so let me summarize my work. So first, we come up with an algorithm to compute the expectation value of an arbitrary polynomial of holonomy and flux with respect to the T-mass coherent state. And taking advantage of this algorithm, we compute the expectation value of the Hamiltonian operator with respect to the homogeneous and isotropic coherent state. And the result up to the next leading order correction is obtained. And also we studied the effective dynamics and to see its relation with the mu-bar scheme in LQC model. So the result is that, so consider the next to leading order correction, the critical density will be bounded from up. And there are actually some works, some further works to do with this framework. So for instance, we can apply this algorithm to consider other symmetric reduced model like a black hole or Bianchi type cosmologies. And also we are going to compute the matrix element of the Hamiltonian operator to study the quantum dynamics. And also, so I think there are still some works on studying the cosmological consequence of the effective dynamics with the next to leading order correction, because if we just consider the toy model, so there will be a recollapse, so which is actually physical undesirable from some perspective view. Okay, thank you for attention.
Thank you for your talk. Are there any questions? I don't see any raised hands, so let me ask a question. Are you aware of the work of Ligner and Rudnicki? They also proposed some algorithm to calculate, as far as I understood, the next to the leading order of the expectation value of the Hamiltonian in the coherent states. And can you compare what are the differences between your approaches, your algorithms?
Yeah. So I also read their works, and I think there are several differences. So at first, in their work, so they just get the result of the Euclidean part, with respect to the coherent state to the next to leading order, and for the Lorentzian part, they get the result. Of the leading order, but they didn't get the result of the next to leading order. And also for the algorithm, so the difference between the algorithm, I think one of the big difference is the algorithm to compute the expectation value of any monomial of flux and Holonomy. So we use how to say, so I think in their work, so they compute the expectation value of this monomial by using the commutator. So for instance, if inside this operator there are the flux which are the flux operator with index plus and minus 1. So by their algorithm, they need to compute this by using commutator between this p plus and minus 1 to reduce it to be the operator of p0. But in our algorithm, so we can compute the expectation value of any monomial of flux and Holonomy directly. So we don't need to consider the commutator between them or something like that. And and also in their algorithm, I think their computation can get result by some recurrence relation. So it's like you get a result with one flux operator, and then you can get a result with 2 flux operator, and then 3 flux operator, and so on. But in our computation, so our algorithm can compute this expectation value directly. So this is 2 difference I know so far. But for further, I didn't have any other So this is the two difference I know.
Okay, thank you. Any more questions? So let me ask one more question. So your code seems to be quite substantial, and how did you check your code that it's working properly? Did you compare to some other known results?
Okay, so the first, so we have several. I think we have several points which can be check our code. So at the first, so we compare the result of the leading order, so given by our code, to with the known result, and it is coincide. This is the first point, and the second point is that, so when doing those computations, so let us go to this page. So for instance here, so there is the summation over edges and the vertices. So there are a lot of terms here, but because of the homogeneity and the isotropy, so some terms with respect to some vertices, with respect to different vertices and edges could have some symmetry. So that means like for instance, if you consider the operator of this associated to edge E1, and also consider the operator this associated to edge E2. So the result, so if this edge E1 and E2 have some symmetry, so they can be, for instance, they can be related by rotation. Yeah, and then the expectation value of these two terms with respect to these edges could also have some relation. So this can be derived analytically, and our code, and then we just check the result obtained by our code to see if there are those symmetries. Yeah, so this is another point to check the result of our code.
Okay, thank you. Thank you. Thank you again for your presentation. And we will now go to our next speaker, who will be Eugenia Cola-Franceschi. And she will talk about holographic maps from quantum gravity states as tensor networks. Could you share your screen with us?
Yeah, of course. Okay.
Okay.
Do you hear me?
Yes, yes, I hear you. Although there is some.
Okay. Okay. So hi everyone, and first of all, thanks to the organizer for giving me the opportunity to give this talk. And so I'm presenting. I'm a PhD student of the University of Nottingham, and I'm presenting the work done in collaboration with Gonfredo Pirco and Daniele Oriti on holographic properties of bar-to-boundary maps in quantum gravity states in the language of tensor networks. So I will start by providing some motivations for our work. Then I will present the framework, which is the blue field theory approach to quantum gravity. Then I will define the bar-to-boundary maps in this context, and I will explain how we can investigate the isometric character of these maps, and then I will conclude with a summary of results and outlook. Okay, so let me start by saying why we are interested in holography very briefly. So first of all, holography arises in several quantum gravity contexts, black hole physics with the area law for the black hole entropy, but also in the anti-de Sitter conformal field theory correspondence, and in particular in this context, the clear manifestation of holography is the Rita-Kayanapi formula, which relates the entanglement entropy of the boundary to the area of a minimal surface in the bulk, in the dual bulk. And so the other reason is that holography is intimately related to entanglement, which in turn seems to play a crucial role in the emergence of space-time geometry and topology. In fact, quantum many-body systems exhibit holographic behavior thanks to their entanglement properties, and therefore entanglement seems to be the origin of holography. And on the other hand, as I said, there are several hints that entanglement is crucial to reconstruct a quantum gravity geometry from fundamental discrete entities at the quantum level. This scenario suggests that we can get useful insights on the problem of quantum gravity by better clarifying the interconnections between these concepts. And the way to do it is to investigate holography in quantum gravity models, which involve entanglement at the structural level. Now, a context like this is exactly the group field theory approach to quantum gravity. I'm going to provide more details later, but for now, let me just say that group field theory is intended as a quantum field theory of space-time, not defined on space-time. The elementary quanta, this field theory, are quantized simplices, which are dual to spin network vertices. And therefore, the theory has the same fundamental degrees of freedom of loop quantum gravity, but organized, as we will see, in a different interspace. The crucial feature that is useful for this discussion is that is the entanglement among simplices that gives rise to spatial manifold, so to spin network graphs. And we will see that this feature is at the basis of the correspondence with the quantum information tool of tensor networks, which is a very efficient tool to study entanglement in many-body physics. In fact, we are going to exploit tensor network techniques for our calculation. So our main objective is to study the holographic character of maps defined from quantum gravity states in this group field theory approach, maps from the bulk to the boundary. In particular, we are going to study their isometric character. In fact, isometry is a necessary condition for holography, as we want that, for example, expectation values are the same in the bulk and in the boundary theories. So the three main steps of this analysis are the following. So first of all, we will see that quantum gravity states associated to open spin network graphs can be regarded as maps from the bulk to the boundary. Then we identify the conditions under which this bulk to boundary map is an isometry, and then we will analyze the isometric character for specific classes of states which correspond to random tensor network, exploiting therefore tensor network techniques. Okay, so let me introduce the group field theory approach in more detail. So is the theory of a field, which is defined not on space-time, but on an abstract group manifold. And the field, the fundamental field excitation is a quantized simplex, so a spin network vertex. So we have a group variable attached to every link, which is dual to a face of the simplex. In this picture, we see the group representation on the left and the spin network representation on the right, which we have the spins and the corresponding magnetic numbers associated to the open edges of the vertex, and the interplanar quantum number, which follows from the recoupling of the edge spins. The group field theory model is defined by an action. In particular, the fundamental features are that the kinetic term provides the performs the gluing of the simplices, namely the spin network vertices, to build up simplicial complexes which are dual to spin network graphs and are therefore interpreted as discrete spatial geometries. And then we have the interaction term, and the interaction processes of these fundamental simplices give rise to higher dimensional simplicial complexes, which are spin forms, namely histories of spin networks. In fact, we see that the perturbative expansion of the path integral for the group field has Feynman amplitudes which correspond to spin form amplitudes. The group field theory as a candidate theory of quantum gravity, first of all, allows to exploit quantum field theory tools in the formulation of quantum gravity theory, because we can go beyond the perturbative expansion. We have connections with several approaches to quantum gravity. I already mentioned that the field theory has the same that is of freedom of quantum gravity, the same kinematical state, gives rise to Feynman amplitudes which are spin form amplitudes. But also there is a connection with quantum Legge calculus and quantum dynamical triangulations, and can also be seen as a generalization of matrix and tensor models, because we have the same combinatorial structure, but with additional group data associated to them. And then another feature that I want to emphasize, because it's crucial for our work, is that this framework allows to import quantum information and convex matter techniques. And why? Because the quantum space geometry, space-time geometry in this context is described as a quantum many-body system, in which the single particles are the spin network vertices. And in fact, the crucial point is that spin network graphs arise in this context as pattern of entanglement among vertices. So has a pattern of entanglement in many body states. And here I'm going to provide more details on the construction of the states. So first of all, the Fock space of the Hilbert space of the theory is a Fock space constructed out of a single vertex Hilbert space. Here we see the vertex, the wave function associated to a single vertex, and the decomposition in the spin network basis that we are going to use in the following. So I briefly mentioned it before. So thanks to the Peter-Weil theorem, a function of the copies of the group can be expanded in spin network basis wave functions, and so we basically have spins associated to the edges, magnetic numbers which are spin projections, and the interplanar quantum number that derives from the recoupling of these edge spins and follows from the gauge invariance at the vertex. So now the state of spin network graphs, so the state of a V connected vertices connected according to a certain pattern gamma, can be constructed in this way. So starting from the wave function for a state of V open vertices, and then gluing them in the sense of entangling the degrees of freedom on the open edges according to the given pattern. So again, this pattern of entanglement is the spin network graph underlying the many-body state. Now I'm going to explain how to regard this state as maps from the bulk to the boundary, exploiting the formal correspondence with the tensor networks. So let me introduce the tensor network formalism. So the a tensor network is basically a set of tensors whose indices are contracted according to a certain pattern. Now, the single tensor can be depicted as a node with a link for each tensor index, and the contraction of indices is depicted as the gluing of nodes. This is a quantum information tool, particularly appealing from a quantum gravity perspective, because first of all, there is a strong connection between geometry and entanglement, because tensor networks encode the entanglement structure of many-body states in the geometry of the network. And also because they are a very efficient tool to simulate the quantum many-body physics, and so can be applied to when we try to consider the continuum limit of these models. We are going to focus on a particular type of tensor network, which is the one called projected entangled pair states, in which the network is constructed by projecting tensor states into maximally entangled states, which play the role of link states. So here we have the example of the connection of two nodes, by projecting their states into the maximally entangled states of open edges. Now, consider the state of the group field theory state associated to a certain graph, which is constructed from vertex wave functions glued to each other thanks to the projection on maximally entangled states of the open edges according to a given pattern. And we can see that this cross-section is effectively a tensor network, a project entangled pair state. So we are going to focus on this type of states, and in particular we're going to consider the case in which these vertex wave functions are chosen randomly according to a uniform probability distribution, and this allows us to exploit random tensor techniques. So now, to move from the concept of state to that of map, let me first explain how this works just for tensor networks. So when we regard all the degrees of freedom of a tensor, all the indices as output indices, the tensor accounts for the state of a quantum system, which lives in the Hilbert space associated to the links at the edges of the output edges. However, we can consider the partition of these tensor indices in set A as input, that we consider as input indices, and the set B, which is the output indices. And in this case, the same tensor can be regarded as a map from the Hilbert space associated to set A to the Hilbert space associated to set B. And so we are going to apply the similar argument to our group field theory states. However, let me stress that due to the gauge invariance at each node, actually we cannot consider without any assumption a bipartition of the degrees of freedom associated to an open spin networks. Because due to the gauge invariance, the various degrees of freedom are not independent. So in particular, we want to regard the intertwiners as input degrees of freedom and the boundary edges as output degrees of freedom. But we can consider them independent at an effective level only when we fix the spins attached to the edges. And so this is the assumption we are considering here. So in this case, the lives in the tensor product of the Hilbert space is associated to the we call it the bulk Hilbert space, the Hilbert space for the set of interfinals of the graph, and then the boundary Hilbert space for the representation spaces associated to the open edges. Now, this state, in the moment in which we regard the interfinals as input and the boundary as output, is just a map between these spaces. Here there is a picture in which the green input lines are the interfinal degrees of freedom, and the red lines are just the boundary edges, which whose degrees of freedom are considered as output of the map. So now we therefore have these bulk to boundary maps associated to our spin network graphs, and then we want to see under which conditions this map is an isometry. When we write the state in terms of the components of this map in the bulk and boundary basis, we see that the map is an isometry if and only if the reduced bulk state is maximally mixed. This means that we can check the isometry condition by computing the entanglement entropy of the reduced bulk state and see if it is maximized. So we perform this entropy calculation in the case in which our graph state is a random tensor networks, and as we're going to see, this allows to us to exploit random tensor techniques, and the fact that we use to compute the entropy, the second order Rayleigh entropy, will result in mapping this entropy calculation in the evaluation of an easy model defined of the same spin network graph. So this is the generalization of a random tensor network techniques applied by Eden and colleagues in a paper of 2016. So the idea is that the second order Rayleigh entropy, that when applying the replica trick, is computed as by these two quantities, zeta1 and zeta0, in which we have two copies of the wall state, and if we are interested in the entropy of the state reduced to a certain region A, we just apply to zeta1 an operator swapping the two copies of the Hilbert space associated to this region A. And since we are considering a random tensor networks, so states in which the wave function associated to the vertices are random, we compute the typical value of this entropy. And we are going to see that in the high spins regime, these two quantities, zeta1 and zeta0, are actually the partition function of an easy model defined on the spin network graph we are considering. And so this entropy is actually given by the free energy cost of a fluctuating domain wall in this easy model. So I will just provide a few details on this calculation. So here we have the quantity zeta that can be zeta1 or zeta0 depending on the presence or absence of this swapping operator here. So the crucial point is that the randomization return a set of Ising spins, one for each vertex, which controls the presence or absence of a swapping operator on that vertex. And then we have additional spins called pinning fields, which are associated to all degrees of freedom of our state and contain the information on the degrees of freedom that we are probing in the computation of this entropy. So for the zeta1, for example, since we are going to consider the reduced bulk state. So the swapping operator acts on the interfiners. All pinning fields for the bulk are equal to -1. While the other pinning fields are all equal to +1 because we are not probing the boundary degrees of freedom, and in θ0 we are not probing any degree of freedom. So thanks to this randomization, this quantity is a partition function of an Ising model, and here we have the Ising action. So in particular, we have the contribution for the links with dj is the dimension of the head spin, and here we have the contribution of the interaction between the Ising spin and the intertwiner, which is proportional to the dimension of the intertwiners. So
I'm sorry to disturb. You have around 3 minutes.
Okay, thanks. So will be very brief. In this homogeneous case, we can put in evidence this term, which is the logarithm of the edge dimension, and plays the role of the inverse of an Ising temperature. So we have that in the high spins regime that we are considering, we are actually probing the low temperature regime of this Ising model, and so the partition function is dominated by the lowest energy configuration. So for θ0, we have all the pinning fields pointing up, and so the minimum energy configuration is the one with all Ising spins pointing up as well, and the free energy is 0. For θ1, we have to flip down the boundary spins, and we see that the configuration in which all Ising spins point up is actually the one which returns the maximum entropy for the reduced bulk state. This means that the condition for the isometry of the map is actually equivalent to the stability of the configuration with all Ising spins pointing up. And so here we just write the condition in a more transparent way by introducing the region, explicitly the region in which the Ising spins are pointing down. Then we focus on the specific case of graphs made of 4 valent vertices, because it's the one of interest for quantum gravity, for the quantum gravity model, and we see that this is always violated for our assumption. This means that back-to-boundary maps for homogeneous graph made of 4 valent vertices cannot be isometric. And then in the inhomogeneous case, of course, there is no more just the combinatorial aspect, but we have the contribution of the dimension for the edges and the intertwiners. Again, we focus on the 4 valent case, and in particular, we rewrite the dimension of the intertwiner in order to introduce this parameter, which controls the spread of the spin assignment. In fact, is the difference between the maximum and the minimum spin associated to a vertex. From this stability condition, we therefore see that, well, in the case in which this spread is 0, so we are back to the homogeneous case and the stability condition is never satisfied, while if the spread is maximum, so there is a high order of inhomogeneity, the stability condition is always satisfied. So let me summarize the results. So we have seen that quantum gravity states associated to open graphs can be regarded as back-to-boundary maps. That these back-to-boundary maps are isometric only if the reduced bulk state maximizes the entanglement entropy. And then we analyze the isometric character of these maps for random tensor networks, mapping the entropy calculation to the evaluation of the free energy of an Ising model. And what we have seen is that the back-to-boundary map for the homogeneous graph made of 4 valent vertices cannot be isometric, while for inhomogeneous graphs, when we increase the range of possible spins, we are actually increasing the holographic character of the map. And well, there are several directions in which this work can be generalized. First of all, by considering quantum states which are not tensor networks, because we consider the strong assumption of having a vertex wave function glued together, but we can have arbitrary correlation among the vertex degrees of freedom. Consider superposition of graphs, which is of particular interest when looking at a coarse-graining procedure. And so we can ask if this isometry from bulk to boundary can be recovered at an effective level. Then exploit this framework also to study the space which is induced on the boundary, and check if it corresponds to a Fock space for the boundary links. And finally, to use these random tensor methods to compute the entanglement entropy of the boundary and see under which conditions we recover a Hbac formula, and in particular its corrections due to the effects of the back entanglement. And this is actually something we are actually working on, in particular to see under which conditions the bulk entanglement gives rise to a region in which the Hbac surface cannot enter, which means that this region would behave like a black hole region. Okay, thanks. Sorry.
Okay, thank you. Thank you for your presentation. Are there any questions? Hannah, please.
Let me unmute myself. First of all, thank you for the very nice talk and for actually very fascinating work. I have a simple question, and this is probably because I don't know this stuff very well, but you made central in this talk this condition that the bulk to boundary map be an isometry. And I was just wondering if you can explain a little bit more why you really want this, because I mean, the little I know about the ADS CFT correspondence says that it's actually a kind of a complicated map between endpoint functions of two different quantum field theories. So I'm just saying, even if this is not an isometry, that doesn't mean that it's not interesting, because the map could be sort of more complicated.
No, yeah, of course. The idea here is just because we are, I mean, the final point would be to see if, for example, we can map bulk observables to boundary observables. So our first, the first requirement would be to have an isometry in order to preserve the expectation values of these observables. So this is, of course, a very simplified framework with respect to the ADS CFT correspondence. First of all, because we are working just at the kinematical level, so we did not implement the dynamics yet. And so this can be regarded as a very basic requirement on this map and this simplified framework. And I imagine that when implementing the dynamics, this map can, of course, become a lot more complicated, and so exhibit other features or be subjected to other constraints.
Thank you.
Okay, thank you. Thank you again for your talk, and it is now time to switch to our last speaker. Our last speaker is Igor Kanatchikov. And could you stop sharing, or? Let me help you stop sharing. So okay.
Thanks.
You're welcome. And Igor, do you hear us?
Yes, I do. Please, I need 1 minute to download that file.
Okay.
Then I will share it.
Okay.
Sorry.
Okay, now I see your slides.
It's fine now?
Yes, yes, it's fine. Okay, so are you ready? Technically.
Yes.
Okay, so Igor Kanatchikov will tell us when the Minkowski spacetime forms. Please go on.
Okay, so I want to remove your pictures here. Okay, so I will talk from the point of view of approach, which is different from loop quantum gravity and other approaches existing. It is kind of approach of its own, which I call pre-canonical quantization. But surprisingly, it gives some interesting results. First, I will outline what I mean by pre-canonical quantization. Many of you have already heard it, but so I have to repeat it, because I don't think it is kind of textbook knowledge yet. Then I will show, so I will basically show what is pre-canonical quantization and how it can be applied to field-bound gravity. And in the course of pre-canonical quantization, we have to introduce a new ultraviolet scale kappa, which I will specify in the end. Then I will discuss a solution of the derived pre-canonical Schrödinger equation for quantum gravity, which would correspond to the quantum version of Minkowski, or to the quantum states which corresponds to the Minkowski space-time, in the sense that expectation values of the spin connection are 0. And then it will be derived that the scale at which quantum fluctuations of space-time are becoming noticeable is related not only to the Planck scale, but also to the scale kappa. In order to understand what is kappa, I will also mention our recent work on the mass gap, estimation of the mass gap in quantum gauge theory, which shows that actually kappa is related to that scale. That is, it is at the subnuclear level. And then it will be based on the solutions and this estimation of the value of kappa related to the scale of the mass gap in gauge theories. We will argue that actually the scale where the forming nature of quantum space-time pops up is several orders of magnitude below the Planck scale, which is the naive expectation from loop quantum gravity or string theory or some other approaches which are discretizing space-time in a sense. So just about motivation of pre-canonical quantization. One can at least have an impression that most of the problems of reconciliation between fundamental principles of quantum theory and general relativity, which is the basic problem of quantum gravity, are related to the distinguished role of time, which we see both in the formalism and quantum mechanics, where it is inherited in certain sense from the canonical Hamiltonian formalism, which underlines both our understanding of quantum field theory as an infinite dimensional system evolving in time, and propagates also to different formulations of canonical quantum gravity. One can even argue that the trace of it are noticeable in the path integral formulation. This canonical Hamiltonian formalism obviously restricts us to globally hyperbolic space-time, and we can't expect that quantum fluctuations would respect that. It leads to difficult functional analysis problems related to the infinite dimensionality and lack of unique representation of canonical commutation relations. It leads also to the ill-defined Wheeler-DeWitt equation, the infamous problem of time, and even to the interpretational issues related to the notion of the quantum state of the universe. So what one can do? One can try to understand fields not as infinite dimensional systems evolving in time, or not as field configuration, initial data evolving in time, but in terms of certain Hamiltonian-like description of fields in space-time, intrinsically in space-time, without separating space and time variables. I must point out that the techniques of the covariant phase space, which became popular recently, also essentially belong to the later, because they need some kind of covariant space-time decomposition, foliation in space-time, that is global hyperbolic structure. So the opportunity is provided by the theory known in the calculus variations as the Donder-Weil theory. It is very easy to think when we have a Lagrangian, which is function of fields, field variables, first derivatives of fields and space-time variables. We can define such objects called polymomenta, the analog of the Hamiltonian function, which will be a function on a finite dimensional space of field variables, polymomenta in space-time. And in terms of those new variables, early Lagrange field equations are written in such a beautiful space-time symmetric form, which more or less describes the fields as sections in a finite dimensional bundle of polymomenta fields and space-time, which is a field theoretic analog of the extended phase space in mechanics. It's quite interesting to notice that actually the Nambu-Goto string and the Einstein-Hilbert Hamiltonian Lagrangian without the high derivative surface terms are actually regular theories in this formalism. So then the problem was, of course, to define Poisson bracket. It can be defined if one identifies the analog of the symplectic structure in this formalism as what I call the polysymplectic form. And it is not very unfamiliar object. In fact, it is just integrand of the expression which gives the symplectic two form in the covariant phase space approach. In fact, if we take the polysymplectic form restricted to the surface of initial data and then integrate over it, we obtain the standard symplectic form. So we just act without integrations, without functionals, and we're trying to go as far as possible along this path. So one can notice that the polysymplectic form can define map between forms which we play the role of observables and multi-vector fields, and that allows us to define the Poisson bracket, the analog of the Poisson bracket operation in the following way, which leads to the structure of the Gerstenhaber algebra with respect to the bracket, graded Lie bracket operation and the natural product of forms called coexterior product, for which the map above given by the symplectic form is possible. It is actually a very restricting class of variables. Still enough for quantization, as we will see. In terms of those brackets, one can write the Hamiltonian field equations and the Donder-Weil form, and also construct the brackets, the fundamental brackets, the bracket between the simplest variables, which generalize the Heisenberg subalgebra of Poisson brackets in mechanics. And one can show that by quantizing those brackets, one can find representation of operators in terms of the Clifford algebra valued partial differential operators in the space of fields. The wave functions will be functions on our configuration space. That means space of fields and X mu's. And in order to have dimensional consistency, we have to introduce the quality kappa, which has the length of inverse spatial volume, which, as it follows from the representation of the differential form omega mu, which is just a set of n minus dimensional volumes of codimension 1 in terms of the gamma matrices. So one can see that dimension of kappa is inverse spatial volume. That is, kappa represents a new ultraviolet scale. Naively, one could expect it to be of Planck scale, but in fact, it turns out to be not the case. Maybe disappointingly, maybe surprisingly, so one has to figure out. Then one have to find out what is the analog of the Schrödinger equation for this precanonical wave function. This is this Dirac-like equation, which satisfies certain requirements, natural requirements, where H is the operator corresponding to the von der Waal Hamiltonian function. So one can see that there are conservation laws, that there is interesting property that the expectation values are satisfying the analog of the Ehrenfest theorem just because of the properties of the evolution of the precanonical wave function given by this equation. And that even in the quasi-classical limit, if we use such ansatz, which is natural generalization of the quasi-classical ansatz, one can obtain the analog of the von der Waal analog of the Hamilton-Jacobi equation, which was introduced in the 30s by the Donder and later discussed by Weil in 1934. Okay, so if we have strings, sorry. So for scalar fields, the von der Waal Hamiltonian operator has this form, and it allows to reproduce certain results from quantum-free scalar field theory, which I guess I will not discuss. I just want to point out that the multi-particle aspects are reproduced from the natural green functions of the precanonical Schrödinger equation. If we consider this green function as 2 by 2 infinite matrix, then it's permanent, and the components of it permanent will actually reproduce the multi-particle amplitudes. One can also discuss, and many of you remember that from my previous talks, that how the canonical functional Schrödinger representation, so in the case of scalar field theory, it is written here, it can be derived from the precanonical description in the limit when kappa goes to infinity, or more specifically, when kappa is identified with the delta at special equal points, delta of 0. So in fact, the formula which relates Schrödinger functional with precanonical wave function restricted to the Cauchy surface, psi sigma here, is given by the expression which is known also as the product integral. This expression makes sense only in this limiting case when gamma 0 kappa is mapped to the I would say untruncated ultraviolet cutoff, which is delta of 0. So it means that standard quantum field theory can be considered as a singular limit of the quantum field theory based on the precanonical quantization. So if we go to general relativity, we can start from the Palatini action, proceed according to the von der Waal Hamiltonian theory. We will get constraints. Those constraints, one can argue, are second kind. That is, in order to analyze them, so we introduce differential forms associated with constraints. We calculate brackets of those differential forms, found that one of them doesn't vanish on the surface of constraints. So we have to define Dirac brackets. Dirac bracket, the definition of Dirac bracket involves the matrix of pseudo-inverse, because we're working on the Grassmann algebra without division. So we have to introduce pseudo-inverse to define which is consistent, can be done the calculation, which leads to the very simple brackets. This leads to the representation of operators of Vielbeins in terms of the partial derivatives with respect to the spin connection coefficients. And gamma underlined are flat Dirac matrices. Gamma with Greek indices are curved the Dirac matrices, but not depending on space-time variables, because they just coordinates of the bundle, of the frame bundle over the space-time. So we obtain in this way the expression, explicit expression of the Donder-Weil Hamiltonian operator corresponding to the Vielbein gravity. The covariant analog of the Schrödinger equation is obviously should be like that. In fact, there is paper which shows that it is that in the case of curved space-time scalar fields, one can derive the standard functional representation of quantum scalar fields on arbitrary curved background, if this is the right equation in curved space-time. So it makes sense to a certain extent. So the Dirac operator, which involves Vielbeins, which are operators, so becomes kind of operator of the Dirac operator or quantized Dirac operator. This notation means that the spin connection coefficient, matrix acts on the Clifford algebra wave function via the commutator Clifford product. That was kind of an important find a few years ago. One can define the measure. We have to consider measure which invariant measure which involves integration over the spin connection coefficient. Then we show that we can argue that one needs the Vielbein coefficients to make it densities to make it invariant, and those densities are operators. So we are arriving at operator valued invariant density over the spin connection space. That allows us to define the scalar product of those Clifford algebra valued wave functions. The immediate bonus here is that because of the normalizability requirement for the wave function, one actually excludes the situations when the spin connection is very high. That is, probability amplitudes of those configurations is increasingly small. In this sense, this is the realization of the quantum gravitational curvature singularity avoidance, which is the common expectation from quantum gravity theories. Here it is done simply, obtained almost for free. And of course, as the result of such description, quantum geometry is described in terms of the probability amplitudes of going from one point with certain value of spin connection to another point with another value of spin connection. So one can call this interesting geometry the spin connection fold. One can argue that those equations actually on average reproduce the Einstein field equations. And now let us consider the simplest solution. The simplest solution corresponding to the Minkowski space in Cartesian coordinates when the spin connection coefficients are 0. So when they're 0, the quantum gravity, our covariant Schrödinger equation becomes relatively simple. One can substitute here plane waves and find the following relation between k mu's, which are modes along space-time, and pi's, which are analog of momentum for the modes along the spin connection dimensions. Then it follows from here the following dispersion relation, rather unusual and maybe even looking complicated, but one can still handle it. So we can Fourier decompose arbitrary solution of this type. The normalizability which involves this curious operator, which is differential operator in this case, in spite of the negative degree, it is actual differential, still high differential operator with respect to the spin connection. So this is the normalizability requirement. We are restricting ourselves to the subspace of vanishing spin connection, so that we are describing the quantum analog of the Minkowski space-time. Then one can require that the expectation value of the metric tensor operator, which is given here.
I'm sorry to disturb. 3 minutes are left.
Yes, I think I will manage, maybe will. Okay, so we have such requirement that the expectation value is Minkowski space-time. And then from those requirements, we derive that the plane waves satisfy such a dispersion relation. The modes propagating along the dimension of space-time are null, like. This gives you a basically the description of the state, quantum state, which corresponds to the quantum to the Minkowski space-time. That is like modes along space-time dimensions, 4 massive modes in the direction of the spin connection space. Some of them spatial-like are tachyonic. What is important is that the scale of those modes is given by this expression. So it is involving Planck length and the scale kappa, which was introduced by pre-canonical quantization. This is the scale where the quantum formness of space-time will appear. What can we say about the scale kappa? It was observed in my my work several years ago that if one quantizes pre-canonically pure Young-Mills theory, this is the expression of the Donderweil Hamiltonian operator for pure Young-Mills theory. Then one can estimate this operator in the case of SU2 Young-Mills with 3-dimensional potential, that is, we work in the temporal gauge till the temporal components, and then estimation is given by the following formula, where AI is the numerical value of the first derivative of the Airy function. And that also leads to the estimation of the gap between the ground state and the first excited state given by the following formula. 0.84 comes from the roots of the Airy functions. There is a rather complicated sequence of estimators, so in the end one can reduce the problem to some problem solvable in terms of Airy functions. So in this way, we see that if one assumes that the gauge coupling is around 1, then the scale of the mass gap, which we know to be of the order of 0.1 gigaelectron-volt, is actually coinciding with the scale of the parameter kappa, which was introduced by pre-canonical quantization. In this way, we see that the scale of the modes, of the oscillations in the direction of spin connection space, which is the scale where the Minkowski space-time becomes fuzzy or foamy. It is actually not Planck scale, but the scale which is known as great unification scale. Surprising combination between the Planck scale and the mass gap scale. So this is basically the result. And I think that could be used, that at some stage, maybe if loop quantum gravity or string theory could be falsified in 1,000 years, then my theory could be falsified maybe in 900 years when those energies will be reachable. Of course, it is a joke because I firmly believe that those fluctuations are seen in the sky in the ultra large scale distribution of matter in the universe, which is kind of, I would say, at the above 1 gigaparsec scale. Okay, thank you very much.
Thank you. Thank you for your talk. Are there any questions? I don't see any raised hands, so let me thank Igor again for delivering his talk, and let me now thank you. I would like to also thank all the speakers of our session, and I would like to close now our second and last loop quantum gravity session. Thank you again.